Is it still raining outside? All right, today we're going to do 2-3, the precise definition of a limit. Because I'm giving you an apology here because the next couple of sections are going to require you to do proofs of a limit existing. You know what I said last time? If I ask you to do a limit, just plug it in there and see it works. No, because the fact that a limit doesn't have to exist, it has to approach a value. We have to now prove that that exists. That's true. And that's what this part's about. So let's begin with the definition. So let our function f of x be defined on an open interval containing c except possibly at c. The function has to be defined on the interval. And there's a c value inside there, but that the function doesn't have to really exist at that c value. It just has to be within that interval. Because this is going to be the crux of what we're trying to do here. The limit of our function f of x as x approaches c is the number L. That's a lot of writing, which now we'll summarize. So the limit of our functions, it's written this way. The limit of our function f of x as x approaches c is equal to some value L. This is how we're going to do it, how we're going to find our limits. But now we have to prove it, what this really means. And this is, I'm going to show you some pictures of what it means and why it doesn't have to exist at the point. It simply has to approach it. So it's saying here's, this is true. This is true if for every number epsilon greater than 0, epsilon is any number you pick, but it's going to be very, 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 very small. And I'll show you what they mean in a second. If for every epsilon greater than 0, there exists a corresponding number delta greater than 0. This is epsilon. This is delta. Such that this is going to happen. Okay, so that's true for every epsilon greater than 0. There exists a corresponding number delta greater than 0, such that this is our proof. The distance from our function to our limit value is less than some epsilon when the distance, the absolute distance of our x to our c value is less than delta. This is going to haunt you. If you've seen it, if you've seen this before, you'll hate this. But we have to trudge through it to understand what we're doing here. So let's see what we're talking about. Let's put this stuff into pictures now. Remember, we have our limit of our function as x approaches some value c and it equals L. We have to be in some open interval that contains our value c. Remember, this is our x-axis. And there's our function. So remember, if I give you a limit of a function as x approaches c, how do we find the L value? What we're saying here is that if we just take our value c, plug it in there, we get our limit value. That's what we're saying. So we have our limit value somewhere in our function. So far, so good? Because these are all of our f of x's. These are our y values, our f of x's. So as our x values, as our x values get closer to c, they correspond to the y values. As x gets closer to c, what happens here? These get closer to L. Same thing on the other side. As our x values get closer to c, they get closer, closer to our L value. So that's the reason I said, if we can, our first step, just plug in our value c into our function. If it exists, there's our limit. But it doesn't always work that way. This is where this comes in. Epsilon and delta are both their distances. How do we know their distances? Well, y2 minus y1 is what? That's the distance between the 2 points, how far they are apart. Can distances ever be negative? No. That's the reason it's absolute value. And so if we're here. So because the distances cannot be negative, we never actually have absolute values. But because they can't be negative, they have to be positive. They have to be greater than 0. The delta defines that. So it has to be greater than 0. But can it be equal to 0? Yes. But we don't care about that point. The reason being because we don't care really what happens at f of c. If it works, then that's great. There's nothing to prove there. But what we're interested in is what happens when we can't get to c. When the distance between our x and our c is some distance infinitely small, greater than 0. And that's what we're saying. That's in our open interval. So as this bound becomes very small, the corresponding bound over here becomes very small. So as we get closer and closer and closer to C, what happens to this? It gets closer and closer and closer to what value? L. So far, so good? Now, so let's see how we use this equation. Example 1. Consider the function f of x equals 2x minus 1 near the value x equals 4. What we're looking at here, so it's asking this. Intuitively, it seems clear that y is close to 7 when x is close to 4. True? Y is close to 7 when x is close to 4. If we plug in 4 in here, what do we get? 7. So that's what I'm saying. It's intuitive. How do we put this in limits? How do we put this in the limit statement?
Approaches 4.
As x approaches 4, this is my c value. Very good. F of x is what? 2x minus 1. So actually, let me put this is the limit as x approaches c of f of x. If we plug in 4 inside there, we get our limit. That's our L. So we've just labeled everything. Now let's see how it works in our proof. So let's look at the left side. F of x is 2x minus 1 minus L. L is 7. When x minus, what is our value c? Is 4, x minus 4 is less than delta. So what we're looking at here, where do epsilon delta live? What part of this graph do they exist? Well, the delta is this part. The delta represents how far we are from our C value. That corresponds to our epsilon on the y-axis. So the smaller delta becomes, what happens to epsilon? The smaller it becomes. So what we're looking for is we're looking for a correlation between epsilon and delta. How can we do that? The only way we can find a correlation is if we can make both of these absolute values the same. So let's see how to do this. Inside here, what do we get? We get 2x minus 8 is less than epsilon whenever this is true. So our objective here is to try to get this to be somehow x minus 4. So how do we solve for x? How do we drop the absolute value? When we drop the absolute value, what happens? We can look at it this way. When we drop the absolute value, you get a positive and negative answer. Remember, what we want inside here, we want x minus 4. Now, for this one, we don't need this one. Let's look at that. If we factor out a 2 inside there, what do we get? I'm sorry. So since 2 is a constant, it's positive. Can we take it out of the absolute value? Divide both sides by 2, we get x minus 4 is less than epsilon over 2. So how are epsilon and delta related? So remember, ideally, they're equal to each other. So what happens here is epsilon over 2 is equal to delta. What does that tell us? Remember, delta is greater than 0. It's a small number. So the closer we get to x, how close do we get to the y values? Even closer. That's what this tells us. This proves to us that the limit exists because this is always going to be positive. It's always going to be positive. So however small delta becomes, epsilon is even closer. So the closer we get to C, we get that much closer to L. That's what this is telling us. Because it's a true statement, therefore our limit exists, and it's gonna work for any value x. And does it have to exist at that point? No, because epsilon delta are any value greater than 0. If delta was 0, if delta was 0, what do we know about x? It's exactly 4. So in other words, if we plug in 4 into our equation, what do we get? We get 7, which is what our limit is. It works. That's why we don't set it equal to. We look at how close can we get to it. All right, let's look at another example. Show that the limit as x approaches 1 of 5x minus 3 equals 2. Okay. And don't be a shortcut person, because how would you prove that? The first thing you do is plug it in there, right? That doesn't prove me anything. We have to prove it using the epsilon delta proof. So go ahead. Let's set it up. I'll put the formula down for you. So there's, just plug it in there first and see. Because remember, our objective is we want to get them both to be the same absolute values. So what's f of x? 5x minus 3. Minus what's L? 2 is less than epsilon. What is C? What? So algebraically, let's work this one out. 5x minus 5. What can we do here now? Take out the 5. We have x minus 1. Because that's a constant and it's positive, we can take it out in front. We need to have absolute value of x minus 1 by itself. So what do we do with 5? Divide it both sides. So what does that tell us? It tells us that delta is equal to epsilon over 5. However small delta becomes, however close we get to the value c, our function gets closer and closer to our limit value. Actually, 5 times closer. So that tells us that it's going to exist. Okay, I know you guys are thinking, okay, it's going to give us a solid answer. No, it's giving us a theoretical answer, saying no matter how small our value, our delta is going to be, there's however close we get to our c value, however close we get to it, our functions will get even closer and closer to our limit. That's what we're assured of. Let's look at another example. Oh, let's look at this. Let's look at another thing. Let's solve this one. Let's expand that algebraically. Let's solve for x. Now I'll show you why I'm doing that. So we have absolute value of 5x minus 5 is less than epsilon. So we drop the absolute value sign, we get an epsilon here. 5x minus 5 is less than epsilon. Remember from algebra, we have this. The conversion of dropping the absolute value sign. Okay, now we're solving for x. So we add 5 to both sides. So we have 5 minus epsilon, 5x, 5 plus epsilon. Now, why did I do that? In that case, I believe it was 1, wasn't it? So notice that this interval is symmetric. No matter what our x value is, it's going to be 5 minus that divided by 5 or 5 plus that. So it's going to be symmetric. If this is my value x, it's going to be the same distance. And let's say this was 5. It could be 3 here or 7. So I subtract 2 and I add 2. Will it always be the case? No. Because depending on what kind of function you have and the how fast it changes. If it's symmetric, we have it, it's easy. We can do this, what we've been doing. But what if it's not symmetric? What if we have an x value, let's say this is 5, and we have 3 and 8? It's not symmetric anymore. What happens there? We choose the shorter distance, the shorter delta value. So if it's not symmetric, then we choose the shorter of the two options. Right. Because since this one's bigger, that means we know that this shorter one has to exist in there. But if we took the bigger one, then we don't know what's going to happen out here. So we take only we know what exists for sure. All right, and we'll get to that one in a second. So let's look at some simple ones first. Find the limit of c as x approaches c. Prove these two using the epsilon delta. It's so simple, you're probably getting confused. Let's see how to do this. Let's begin this. Remember, we're using f of x minus L is epsilon, x minus c delta. So what's this graph going to look like? So what the graph looks like, it's going to be a straight line redundant. Identity function, what's the graph going to be look like? It's going to be exactly a diagonal, right? Because y equals x. So no matter what value c you take, so however close we get in our interval, so we have c minus delta, c plus delta, that's going to correspond to f of x minus delta, f of x plus delta. Because our epsilon, this is going to be f of x minus epsilon. This is going to be f of x plus epsilon. In other words, our epsilon is going to be much bigger than our delta. This is what it's telling us. So we have x minus c is less than epsilon when x minus c is less than delta. So what's the relationship there? epsilon equals delta. So however close we get to our C value, we get that close to our limit value. As long as, will it ever equal 0? No, because it can't equal 0. It's gotta be greater than 0. So for any x value, delta is greater than 0, implies that epsilon is going to be greater than 0, and f of x or f of c will equal the limit. That's what it's telling us. How about the next one? What's the graph of the second one? The horizontal line. It's a constant function. The graph of this one will be at k, which is also our limit. So no matter what c value we take, our interval if I take our function minus delta, our function plus delta, we are going to be within this bound. It's always going to exist because it's a constant function. So let's see what happens. So we have f of x, which is k, minus the limit, is less than epsilon when 0 x minus c is less than delta. K minus k is 0. So no matter how close we get to C, how far are we from our answer? We're at the answer. There is no distance away from there. So since that's true, no matter what x you pick, it's going to give us our answer. Next. So those are the simplest ones. Those are the constant and the identity functions. Let's now look at functions that are not symmetric. For the limit as x approaches 5 of the square root of x minus 1 equals true, find a delta greater than 0 that works for epsilon equal 1. So what that tells us is this. We have to find f of x minus L is less than epsilon when 0 is x minus c is less than delta. So we want our epsilon to be 1. So we have the square root of x minus 1 minus 2 is less than 1 when x minus 5 is less than delta. So the first step is we have to solve this side. We have to simplify the left side. Did everybody get on top? So how do we do that? What's our first step? Can we do anything inside there? No. So we have to get rid of the absolute values. That becomes -1, the square root of x minus 1 minus 2. There. That's our first step. Second step. Remember, I told you, calculus is mostly algebra. So we're solving for x. We have to add 2 to both sides, or all 3 sides. So 2 minus 1 is 1. Square root of x minus 1. 2 plus 1 is 3. What do we do in the middle? How do we get to x? We have to square it to get rid of the square root. So we square all 3 sides. 1 is less than x minus 1 is less than 9. Add 1. So it's 2 is less than x is less than 10. So remember, what this shows us is now our interval that our delta is going to be in, our C value is going to be in, is this interval. What is our C value? Our C value is 5. And our interval goes from 2 to 10. Is it symmetric? No. So which side are we going to use? We're going to use this side, right? Oops. So what we're going to do there, we have our function f of x, or f of x minus our limit is less than 1. Whenever we have x minus 5 is less than delta. Now, so what's our delta going to be? Yeah, our delta is how far we are from our C value. The delta here is 3. The delta here is 5. So we're going to use the smaller of the two. So our delta is going to be 3. So what does that tell us? Even though we didn't get the same values in there, what this tells us is this. We have an open interval of radius 3 with or about x equals 5, because that's our C value. They'll be inside the open interval to 10. That's what it's telling us. The reason this one's a little bit different than the other ones is because we defined an epsilon. Earlier, epsilon and delta were simply variables. We can choose them as small as we want. But once we defined epsilon to being 1, we've now all we're looking for now is what is our interval? How sure are we that our value is going to be within there? So, is our C value inside this? Yes. So because it's inside there and we're sure of that, that means our limit's going to exist when we get to 5. Steps to solve for delta. Given our function, our limit, our C, and our epsilon is greater than 0. Steps to solve for our delta, given a function, a limit, a C value that we're approaching, and an epsilon greater than 0. This will involve a delta greater than 0, where the limit, the function of f of x minus L is less than epsilon. We're just stating the obvious here. Using these steps. 1. Solve the inequality f of x minus L less than epsilon to find an open interval AB containing C. Where the inequality holds for all x not equal to C. So remember, the first thing we do is we deal with the left side. That's our step 1. If it's symmetric, then all we have to do is solve inside there so it looks like the delta, the x minus C. Once we do that, we compare the epsilon delta and we're done. If it's not symmetric, then we have to solve it. We have to find the open interval. And then we choose our delta from whatever's the smaller of the two deltas. So our first step is take the left side and find the open interval. Okay, how do we find the open interval? Remember how we did that? We have a delta then we take it algebraically, drop the absolute value sign. So we have negative delta is less than equation, less than, so when we have f of x minus L is less than epsilon, this becomes negative epsilon f of x minus L is less than epsilon. Again, it's all algebra from there. But we're trying to solve because remember, f of x is a function. It has an x value in there. So now we take this and solve for x. And that's going to give us our interval. So that's step one. Again, all algebra. What's step two? Step two, remember, now we have a closed interval or open interval. Step two is says find a value for delta that places the open interval C minus delta, C plus delta, centered at C inside the open interval AB. When that works, the inequality f of x minus L is less than epsilon will hold for all x's not equal to C in this interval. So we have to first find the open interval AB. Once we find A and B, the interval AB, then we find the smaller interval C plus and minus delta. It's got to be inside. This interval has to be inside the larger interval, which is why we use the smaller of the two if it's not symmetric. Prove the limit as x approaches 2 of f of x equals 4 if f of x equals the piecewise defined function So prove that the limit of f of x equals 4 if as x approaches 2, if this function exists. Remember, you don't have to exist because if x is 2, what's the answer going to equal? 4. But we can't use 2. We have to get infinitely close to it. So what do we have to, what we have to show is this. That's what we have to show when x equals 2. All right, so let's begin. Plug in everything. What is f of x? We'll do the first one.
Square.
X squared minus, what's our limit? 4 is less than epsilon when 0 x, what is c value? 2 is less than delta. So let's begin from there. So what we do is the left side. Remember, we always have to first start off with this one. That's our first step. So we have x squared minus 4 is less than epsilon. Drop the absolute value. So that becomes negative epsilon. X squared minus 4 is less than epsilon. Next step. Because we're solving for x. Add 4. So we have 4 minus epsilon is less than x squared is less than 4 plus epsilon. Square root all three sides because we're trying to get x by itself. So square root of 4 minus epsilon is less than absolute value of x. I'll show you why that is important in a second. Why do we have to put absolute value of x? Can't be negative. Because remember, whenever you take a square root of an x squared, the answer is always plus or minus. But because we have radicals here, can they be negative? No. So that's why we have to take the absolute value of it. But because they are radicals, they can never be negative. Do we need the absolute value there anymore? Because now we're restricted. Our domain is now restricted to only positive values of x. So that's my interval. That's my interval. So we have the absolute value of x squared minus 4 is less than epsilon. Holds for all x not equal to our value 2 in the open interval for minus epsilon, square root 4 plus epsilon. That's step 1. We found the interval that we're looking for step 1. What does step 2 tell us? Step 2 tells us we have to find the value of delta. Find a delta greater than 0 that places the interval 2 minus delta, 2 plus delta inside the bigger one.
How did we get 2 minus and 2 plus delta?
because on the delta side, we have solve for x there. Since we solved for x in the first one, we have to do the same thing there. So we have negative delta x minus 2 delta. So it's 2 minus delta equals x is 2 plus delta. Now, because we have this connection here, the connection between epsilon delta, delta is going to be the radical 4 minus epsilon, radical 4 plus epsilon. So we need the smaller of 2 minus 4 plus epsilon and 4 plus epsilon minus 2. The way we do that, we use the min function. In mathematics, we'll use the min function, which is the smaller value of the intervals. So we have the 4 minus epsilon, and they have the 4 plus epsilon. Oops, I'm sorry. Whichever one that is, whichever the minimum of those are, where do we plug it? Where do we put that? Min of is the value we will use for our delta. Because with that, it's now going to make sure that we are on the innermost value, because our x values now will be whatever epsilon is, our x value is now going to be inside there. So because our delta value is smaller, this will assure us that our inner value, c minus delta, c plus delta, is going to be less than f of our L minus epsilon L plus epsilon. Again, it's theoretical. We have to try to find this interval on the x-axis has The closer this becomes here, that means the closer it becomes to our L value. And that's what, this is the interval we have here. That's this one. And the smaller that becomes, these will get even closer. Again, this is what I said. This is why I apologize when we started this, because you're not really looking. I know when you're doing math, you're looking at, I want an x equals 7. It's not going to give us that. It's going to give us an equation that's going to show us epsilon and delta relationship. But don't worry, once it's over, I guarantee you, once we're done with this stuff here, we have a concept of what exactly a limit really means. It starts flying from there. But I do apologize. It's going to be the longest part is doing this stuff on your homework. Now we're not going to do that. That's just a big definition. All right. So that's it for that section.